All right, so now that we have all of this theory and all these definitions, we're going to discover how we can find the absolute, not local, but absolute maximum and minimums. Of course, on a continuous function, defined on a closed interval. Remember, that's the only time absolute max and min is guaranteed for a continuous function on a closed interval. So again, everything's relating back to that definition. All right, we're building concepts here. So let's look at a picture. So let's do a basic graph on an interval from A to B. And it's a closed interval, so we'll have something like this. All right, let's just say this is what our function looks like. So if we were looking at this graph, we see that we have these local maximums, local minimums, right? And remember, local maximums and minimums, those are critical numbers, right? So all of the local maxes and local mins are happening at the critical numbers. Okay, and then of the critical numbers, this is actually our absolute max up here. All right, and then here's a local minimum, here's a local maximum, and then this is actually the absolute minimum and the endpoint. Okay, so when we're trying to find absolute maximums and minimums, we have to check some candidates. The critical numbers, any critical number is a candidate to be an absolute maximum or minimum, but the endpoints can also be absolute maxes or mins. Okay, so when we're trying to find absolute extrema, we have to check the critical numbers and we have to check the endpoints. And that's called the closed interval method of finding these extrema. So let's write that down. So the closed interval method. Okay, so to find the absolute max and min values, maximum and minimum values. And let's restate our hypotheses. We have to have a continuous function. Continuous function. We'll call it f. And then we also have to have it on a closed interval. Okay. And it's a step-by-step process, okay? And let me underline these two important things. We need a continuous function and it has to be on a closed interval. So to find them, first, let's find the values of the critical numbers. And then once we have the critical numbers, when I say value, it's the value on the function f. Values of f, I should say, at the critical numbers. All right, and in the open interval AB. Okay, and then we saw critical numbers is not enough. We also have to check the endpoints. So let's find the values of f at the endpoints, A and B. All right, and then your third step is you're going to compare all the values. So from 1 and 2, find the biggest value and find the smallest value. So the largest and smallest from 1 and 2 are the absolute min and max. Okay, and there you go. So that's the closed interval method. So let's try an example. And we're going to number 48. We're going to number 48. And the instructions is we want to find the absolute max maximum minimum value of the function f of x equals 5 plus 54x minus 2x cubed on the interval 0 to 4. Okay, so first of all, let's make sure we have our hypotheses all out of the way. This is a polynomial. Are polynomials continuous? Absolutely. So we want our function to be continuous. It is, because polynomials are continuous. And 0 to 4, because we have those hard brackets, this is a closed interval. Okay, so that's the only criteria for the to finding our absolute max and min. So what we have to do first is we have to find the critical numbers, and then we can start here on step 1. We can find the values of f at the critical numbers. So we'll have that as our first step. Let's find the critical numbers. And remember, the critical numbers happen when our derivative is 0 and when our derivative is undefined, ud undefined. All right, so let's find the derivative of our function. Let's see, derivative of 5, it's going to be 0 plus 54, and then bring our exponent down. 2 times 3 is 6, and subtract 1 from your exponent. All right, so 54 minus 6x squared is our derivative. So now, first of all, that's another polynomial, that's a parabola. It's defined everywhere. So we're just going to be focused on this one. Where is r? So again, doesn't apply in this situation. So we want to know when 54 minus 6x squared, wherever that's equal to 0, that's going to be a critical number. Okay, so we can solve this a lot of different ways. I'm just going to rearrange this. I like to have the leading term first. We could definitely use our square root property. I'm going to factor out a -6 just to make it a little bit easier. Okay, and then, you know, we can do an x plus 3x minus 3. So my technique right now is using the 0 factor technique, where you make one side 0, factor everything completely, and then set each factor equal to 0. All right, that's a little pre-calc review. All right, so our critical numbers are going to happen at -3 and +3. Okay, and then, you know, conversely, let's talk about it. Why not? You can also solve this using the square root method, where you isolate your squared term like that. Okay, so from here to here, I just added 6x squared. I would divide out by 6 And now the square root property says I can take the square root of both sides as long as I add a plus or minus. So we still get plus or minus 3. All right, so different techniques. Okay, so the reason why we're doing that is we're going to take our critical numbers and we're going to find f of 3 and we're going to find f of negative 3. Okay, because now these are the candidates to being the absolute max and minimum. Those are the candidates for being the absolute max and min. Okay, so f of 3. Let's plug it into our original function. Common mistake is to go back to the derivative. Remember, we're going all the way back up here. So we're going to be plugging in 3 here, and then we're going to be plugging in negative 3. Okay, so 5 plus 54 times 3 minus 2 times 3 cubed. Okay, that ends up being 113. And then f of negative 3, well, look at this, guys. Is negative 3 in our interval? It's outside the interval. So again, just to kind of visualize what's going on, I'll use a different color. We have some function, you know, whatever it is, and we're only interested between 0 and 4, right? Because that's what the problem says. We want to find the absolute minimum on 0 and 4. And then our other critical value was over here at negative 3. So do we care what happens over there? We don't. So this is outside our interval, 0 to 4, so we don't have to worry about it. Okay, so we're done with step 1. Let's move on to step 2. All right, so step 2. Now we have to test the endpoint. So we have to figure out what happens at 0 and what happens at 4. So we'll look at f of 0, the endpoints, and we'll look at f of 4. Okay, so f of 0, if we plug in the x, it'd be 5 plus 0 minus 0. So we're looking at 5. And then we plug in the 4 to the original function. Okay, and if we plug that in, we get 93. All right, so we're almost done. We're almost done. What's left for us to do in step 3 is now we have to compare. So again, remember the critical numbers and the endpoints are the candidates for the absolute min and the absolute max. All right, and so we have to figure out, let's see, we had 113. We have to find the smallest value and the largest value. So we see that 5 is the smallest and 113 is the largest. So we can conclude that f of 0 is 5. So 5 is the absolute minimum and f of 3 is 113 is the absolute maximum. Okay, so there you go. All right, and then that's how we can find the absolute maximum and minimum using this closed interval process.